again, my name is Montoya-Zapata. I'm from Universidad de Delft, Colombia, and I'm working also in Spain, in Técnica. So, first I want to describe our problem briefly. We're given like a complex in large shape, for example, the elephant in the image. And we also have a lattice unit cell, in this case a Kelvin cell, with the main characteristic, that is that it has slender walls. So that then, for example, the side length of that cell is 1.9 millimeters in comparison with 0.1 thickness that has a wall. It's like 20 times its thickness. And the first thing we want to do is, okay, we have the large domain and the unit cell. So we want to model that domain by means of this Kelvin cell. So we obtain something like that. For example, we obtain like a final domain of 14,000 Kelvin cells. And what we want to do is to be able to run different load cases using finite element method. Okay, so what's the problem? The problem is right here. I mean, we have for this elephant 14,000 Kelvin cells, and that will generate something like 6 millions of 3D elements. So actually, we don't have the computational capabilities to be able to run such a simulation. So what we want to do is, or what we did was to simplify our domain. So instead of having a Kelvin cell with those slender walls, we simply say that, okay, we have a set of faces, and each face has a thickness associated with it. But this is from a geometrical point of view. But we also need to think on how will we simulate that domain. So from finite element, we can see, okay, instead of having 3D solid elements, we can use 2.5D shell elements that has a thickness associated with them. And we also try to consider like a more general view by adding some kinematic constraints between the faces. So that this may allow us in the future to model different interactions between the faces of our domain. So, okay. Here, I mean, until now, there are two things that are a little bit like tricky for now. And one thing is the non-manifoldness. Why non-manifold modeling? So basically, we are concerned with a special type of non-manifoldness. And it's here since on a single edge, there intersects more than two faces. So we cannot use traditional data structures to store our geometrical entity. So one of the things that we did was to implement our own data structure that is able to store this geometrical entity. And of course, this is based on traditional boundary representations and the use for cat modeling. But one of the main differences is that at the end we don't have a solid body, instead we have a set of faces. And the other thing is about kinematic constraints. So at this point, up to now, we have only implemented linear kinematic constraints. That is like the faces share like the edge. But like beyond this framework more generally, we could think about modeling other interactions. something like mechanical or like a spring, or adding less constraints to the faces. So, okay, until now, this is more or less what our approach is about. But here, I want to show you how we evaluated our approach. So, we first enumerated some lattice domains, basically 4 domains of 4, 8, 27, and 64 Kelvin cells. And these domains have a main characteristic for us, is that they may be simulated using the 2 approaches, our approach and the approach of using 3D finite elements. We simulated an aluminum with 71 with Young modules of 71 gigapascals and Poisson ratio of 0.3. And our Kelvin cell has a size of 1.9 millimeters and thickness 0.1 millimeter. We carried out actually 3 experiments: tension, shear, and torsion. Here I present only tension and shear, and if you're interested in the paper of the results for a torsion test. So here we have the tension and shear boundary conditions on our domain. In particular, for the domain of 4 phases, we load the phases at the top of our domain, and we constrain the phases of the bottom of our domain. For the case of the tension test, we only constrain in the z direction, so that the domain can move along x and y directions. So here are some results of our simulations. By the way, we use stances for running our simulations. And here I want you to notice two main things. The first one is that look at the color distributions in comparison between the 3D model and the 2.5D model. In both the tension and shear, they are very similar. And the other one, maybe the most important one, is that the magnitude of the displacements between the 3D model and the 2.5D model are this close. I mean, but until now, this is kind of a qualitative results. But we also wanted to have a quantitative result to compare us against the 3D traditional modeling. So using the fact that the color distribution between the 2 domains were similar, we used the maximum displacement in each direction to calculate the relative error of our approach. So here, for the shear test case, in the 3 directions, x, y, and z, we can see that the relative error is lower than 15%. So as for the tension case in x and y directions, but not in z direction. However, we can notice that in z direction, once the number of Kelvin cells increases, the relative error tends to decrease, which is something that we want, because what we want at the end is to simulate large domains. And here is where our approach shows its main advantage, and it is its computational efficiency. So notice the number of elements, the number of nodes, and the memory allocated by the ANSYS solver. And looking in red the 3D traditional model and in blue our approach, and you can see how, I mean, think it's clear how our approach is much more efficient. Okay, so in comparison with the initial elephant that I had shown, so we generated the lattice domain from the original elephant, and we obtained 14,000 Kelvin cells. So in quantitative terms, it means 600,000 elements, 2.5D elements, and 900,000 nodes. And look that in the case of 3D, that would be something like 6 million elements and 13 million nodes. Actually, we cannot even generate the 3D model for simulation. These are some of the results for our simulations. We simulated tension, shear, and torsion. Here, I show only again the tension and shear results. They are purely, illustrative, because at the end we don't have the 3D model to compare us, but at least we could generate them. So, to summarize the advantages and disadvantages of our approach, the main advantage is its computational efficiency, and without losing, of course, it is not perfect, but it's still accurate in comparison to a 3D model. And some of the disadvantages are that in the step of the modeling of the elephant with those Kelvin cells, we lose some information. The high frequency zones cannot be replicated, and the small details are also lost. And we also like to have some laboratory experiments to be able to compare our approach back with real work pieces. So, to conclude, I have presented a methodology to study large and complex lattice domain. It is efficient and still accurate, at least for many indirect stacks, and with relative error under 15%. And the framework can be extended to consider non-linear kinematic constraints between the phases. And we also see a need to generate some laboratory experiments to compare the results against them. And as a future work, as an opportunity to extend this research, we may consider some anisotropic geometries associated with the material, for example, an anisotropic Kelvin cell, so that it is larger in one side in comparison with the other sides. And thank you for your attention.